Picture this. It's the end of a long, exhausting day.
Right.
You pull your electric vehicle into the garage, you shift into park, and you just, hit the power button on the dash.
Like we all do.
Exactly. The massive infotainment screens go dark. The ambient cabin lighting slowly fades out. You hear this reassuring, heavy mechanical clunk from somewhere deep underneath the floorboards.
Yeah, the big relay sound.
Right. You grab your bags, close the door, and walk into your house, completely assuming the vehicle is asleep. Totally inert. Safe.
Well, I mean, it is the assumption every modern driver makes. We've spent decades, being conditioned by consumer electronics to just believe that a dark screen equals a completely depowered machine.
Yeah, screen off means power off. But the reality beneath the floorboards of a modern electric vehicle is it's vastly more complicated and honestly a little unnerving.
Very unnerving. Yeah.
Because what you don't realize as you walk away is that a physical mechanical system within the battery pack might have just, failed to do its one solitary job.
Right. And the stakes there are massive.
Huge. It might have failed to sever a connection that is holding back 400 or even 800 volts and thousands of amps of direct current.
Yeah. Which is an incredible amount of energy.
So the car's digital brain thinks it's turned off, the dashboard is off, but because of this microscopic metallurgical failure, the high-voltage system is secretly still fully live, fully connected, and just completely exposed to the rest of the vehicle architecture.
It really represents the ultimate invisible threat in modern automotive engineering.
And that's what we're getting into today. Welcome to our deep dive. Today, we are undertaking this massive forensic exploration into one of the most critical, highly prioritized hardware failures that can possibly occur in a modern high-voltage power battery pack.
Yeah, in the global engineering community, specifically within the functional safety standards, this failure goes by the diagnostic codes 502 P0AA1, or sometimes P0A2A.
But to the engineers designing these systems, it's simply known as high-voltage contactor welding.
High-voltage contactor welding.
Right. And just the phrase alone, it evokes heady industry, maybe sparks flying in a shipyard. Certainly not something happening silently underneath a family SUV parked next to a lawnmower.
No, definitely not what you want to think about in your garage.
I spent the last week researching this phenomenon, poring through technical specifications, and the sheer scale of the energy we're talking about is staggering. We are going to completely dissect the anatomy of this meltdown today.
We'll explore the physics and chemistry of how and why these heavy-duty metal switches literally melt together.
We're going to look at the incredibly ingenious software algorithms and the actual explosive hardware designed to protect you when this failure inevitably happens.
And we will trace the obsessive, rigorous engineering that goes into preventing it from occurring in the first place. I mean, from the initial design and simulation phase onto the pristine factory floors, all the way into the extreme torture testing chambers where validation engineers deliberately try to destroy these systems.
We really have to go to this level of detail because this specific failure, the inability to cut high-voltage power, it removes the vehicle's primary physical safety barrier.
Yeah, and because of that, global automotive safety standards, specifically ISO 26262, they assign this failure mode the absolute highest risk rating possible, which is ASIL-D.
ASIL-D. Let's contextualize ASIL-D for a minute here. ASIL stands for Automotive Safety Integrity Level. There are different grades, right?
Correct, yeah.
So if your car's radio suddenly stops working or the touchscreen freezes, that might be an ASIL or maybe just a quality management issue.
It's annoying, sure, but
Yeah.
you just pull over, restart the car, and you're fine.
Right. But ASIL-D is the top of the mountain for risk. It means, basically, if this specific system fails, the occupants or the surrounding environment are in immediate catastrophic danger.
And the system must contain absolutely 0 single points of failure. The tolerance for error is practically non-existent.
So, to understand the massive safety nets surrounding an ASIL-D component, we first have to understand the microscopic violence happening inside that battery pack to cause the failure in the first place.
Yeah, we need to look at the first primary root cause. It's a phenomenon known in the power electronics industry as hot switching.
Hot switching. Okay.
Consider the main contactor. At its core, it's just a massive, heavy-duty electromagnetic relay. Its entire purpose is to physically bridge or physically separate the main high-voltage battery from the inverter and the electric motors.
So it's a giant switch.
Exactly. Now, imagine that contactor trying to cut off a highly inductive, massive direct current while the vehicle is actively under heavy load.
So you're like accelerating hard down the highway, the motors are pulling hundreds of amps of power, the current is flowing incredibly heavy, and for whatever reason, maybe a software glitch, maybe a sudden system fault, the switch is commanded to physically open and stop that flow instantly?
Right. And when the mechanical contacts of that switch begin to pull apart, even for a single microsecond, the physics of direct current create a terrifying scenario.
Because it's not like the AC power in your house, right?
No, exactly. Unlike alternating current, which drops to 0 volts dozens of times a second, direct current is a continuous, unyielding wall of energy. It has immense electrical momentum.
It just doesn't want to stop.
No, it refuses to. When that tiny physical gap appears between the metal plates, the electricity, well, the voltage potential is so high that it simply ionizes the gas or air between the plates. It tears electrons from their atoms, and the current physically leaps across the opening gap.
And we call this a DC arc.
A DC arc.
It is essentially trying to build a bridge out of pure plasma. I was reading about the thermodynamics of this, and I was trying to come up with a visual for the listener. It's akin to trying to stop an industrial high-pressure water main by just jamming a metal plate in front of it.
That's a good way to picture it.
But instead of water, the flow is pure lightning.
Yeah, and the heat generated by that plasma arc is staggering.
Yeah.
We're not talking about the heat of a stovetop.
No.
We are talking about localized temperatures, routinely exceeding several thousands of degrees Celsius, generated in fractions of a single second.
That's insane.
It is. And this extreme thermal shock acts directly on the surfaces of the contact materials. The engineers, they don't use standard steel or copper for these contact points.
They use specialized alloys, right?
Yeah, incredibly tough, highly specialized alloys, typically silver tungsten, denoted as AgW, or silver tin oxide.
Yeah, I looked into why they use the specific alloys. It's fascinating. Silver is one of the most conductive elements on the periodic table, so it allows the normal electricity to flow with very little resistance, which is obviously great for efficiency.
Exactly.
But silver is also relatively soft, and it has a low melting point, so they matrix it with tungsten, which is, it's the same metal they used to use in incandescent light bulb filaments.
Right, because it can withstand massive heat without melting.
Yeah, so the tungsten provides the physical skeleton to survive the daily mechanical slamming of the switch, while the silver handles the electrical flow.
That is an excellent breakdown of the metallurgy. But unfortunately, even a matrix of silver and tungsten has thermodynamic limits.
Right.
When that DC arc strikes, the localized thousands of degrees of heat instantly exceed the melting point of the silver within that alloy matrix.
Oh, wow, so it just liquefies.
Literally, the surface of the contact liquefies. You have boiling liquid metal pooling on both sides of the microscopic gap. And as the switch either finishes its mechanical movement or the arc momentarily extinguishes, that liquid silver cools and solidifies almost instantaneously.
And when it freezes back into a solid, it doesn't just dry out, it freezes the two separate pieces of metal together.
Exactly. It forms a flawless, irreversible metallurgical bond. The two separate contact plates have literally been forge welded permanently shut.
That's terrifying.
They are now one single continuous piece of metal. The component is locked in a conducting state, completely and irrevocably destroying its physical ability to ever act as a switch again.
The plasma fire hose literally melts the valve permanently open.
Yeah, that's exactly what happened.
That is a terrifying physical reality to have hiding under the floor. But, hot switching is just the violent breaking of the circuit. In my research, I found that you can cause the exact same catastrophic weld when you were just turning the car on.
Yes.
Which brings us to the second root cause, pre-charge timing failure.
Pre-charge failure deals with how the vehicle's electrical architecture prepares itself to safely receive massive voltage.
Right.
Inside the system, sitting just before the electric motors, is a massive component within the inverter called the DC link capacitor.
Right.
Think of a capacitor not as a battery, but as a giant reservoir that is incredibly thirsty for electrical charge. And it's designed to smooth out the power delivery.
I was trying to find a good analogy for this because the bathtub metaphor you see in textbooks always felt a bit too simple for what is happening at 800 volts.
It is a bit too passive, yeah.
Right. It's more like an industrial hydraulic accumulator. Imagine a giant, thick steel pressure vessel. Inside, there's a rubber bladder filled with high-pressure nitrogen gas. The system uses this vessel to absorb massive, sudden spikes in hydraulic fluid pressure.
Okay, I follow you.
If you just open a massive valve and dump high-pressure fluid into an empty accumulator all at once, the violent shockwave would literally blow the seals out of the entire system.
That is a highly accurate mechanical parallel. Because in the electrical realm, an empty DC link capacitor has an effective resistance of near zero.
Oh, wow.
Yeah, it represents a massive electrical vacuum. If the main contactor were to simply slam shut while that capacitor was completely empty, the sudden rush of electricity from the battery trying to fill that vacuum, what we call the inrush current, would be astronomical.
Because it's trying to fill it all in a millisecond.
Exactly. It would instantly exceed the physical current carrying limits of the relay, creating the exact same extreme localized heat, melting the silver alloys, and forging that exact same metallurgical weld we saw with hot switching.
So the obvious question is, how does the vehicle prevent that violent inrush from happening every single morning when I press the start button to go to work?
It relies on a meticulously choreographed sequencing protocol managed by the Battery Management System, or the BMS.
The brain of the battery.
Right. The BMS contains a highly precise timing algorithm. Before it ever allows the massive main contactor to close, it first closes a parallel, much smaller electrical pathway called a pre-charge circuit.
Okay.
This secondary circuit forces the electricity to detour and flow through a dedicated pre-charge resistor.
Going back to the hydraulic analogy, it's like opening a tiny, heavily restricted bypass valve to let a small trickle of fluid slowly fill the accumulator and build up the pressure safely.
That's spot on. The resistor acts as an electrical bottleneck. It intentionally restricts the current, allowing the thirsty DC link capacitor to fill up smoothly and safely according to a mathematical curve known as an RC time constant.
So it's a controlled fill.
Very controlled. And as the capacitor fills, its voltage rises. Once it's nearly full, the voltage difference between the main battery pack and the capacitor drops to almost zero. The electrical pressure on both sides of the main door is now equalized.
And only then, when the pressure is equalized, does the BMS send the command to open the main floodgate. The heavy-duty main contactor closes, and because there is no massive pressure difference, there's no violent rush of electrons.
Right.
There's no spark, no arc, no extreme heat.
That is the intended, flawless design. However, hardware degrades.
Of course it does.
What happens if that pre-charge resistor has suffered thermal fatigue after 5 years of daily use? Or what if the BMS timer algorithms experience a fault, or a localized control circuit malfunction occurs?
I see the vulnerability here. Because the BMS timer is just software. It might think, okay, 300 milliseconds have passed, the math says the capacitor must be full, but because the resistor is degraded, the capacitor is actually only halfway full.
Exactly. The BMS, operating on faulty assumptions, issues the command to slam the main contactor shut prematurely.
And boom.
Boom. A massive residual voltage difference still exists across the gap. The resulting inrush current hits the metallic contacts like a sledgehammer, instantly exceeding the arc tolerance of the alloys, causing a transient high-temperature event, and once again, melting the contact solid.
Wow. Okay, so we've covered the violent breaking of the circuit and the violent making of the circuit. Both are huge, sudden electrical events.
They are.
But as I was diving into the manufacturing data, I found a third root cause that completely blew my mind. We are moving away from electrical algorithms and sudden plasma arcs into the realm of raw mechanics. The assembly deviation butterfly effect.
The butterfly effect is a very apt description. What is truly fascinating and, frankly, deeply concerning to quality control engineers is how an incredibly minor, seemingly disconnected physical oversight on the factory assembly line can silently evolve into a catastrophic electrical failure thousands of miles and many months down the road.
We are talking about a loose bolt. Just a single physical bolt on a copper bar buried deep inside the battery pack.
Specifically, we are looking at the internal bus bar bolts. Bus bars are the thick copper strips that carry the heavy current between the battery cells and the relays.
Right.
During assembly, if the rotational tightening torque applied to these bolts by a robotic arm or a human operator is insufficient, even if it's just a few newton meters below the engineering specification, it creates a microscopic looseness at the physical joint between the high-voltage relay pins and the copper bus bar itself.
When you say microscopic looseness, I imagine a mechanic wouldn't even be able to wriggle this with a wrench, right? It would look and feel completely solid and perfectly safe.
Oh, to a human hand, it would feel completely structurally sound. But on a microscopic electrical level, the actual surface area of metal-to-metal contact has been significantly reduced.
And that's bad.
Very bad. Electricity, specifically high amperage direct current, requires a massive surface area to flow smoothly. When you constrict that flow through a reduced contact patch, you dramatically increase the contact impedance at that specific joint. Impedance is essentially electrical resistance.
And the fundamental law of electronics is that where there is electrical resistance, there's friction, and electrical friction generates heat.
Right. We refer to it as localized Joule heating, which is governed by the equation current squared times resistance.
The math just doesn't care.
It doesn't. Because the current during fast charging or highway driving is incredibly high. Squaring that number means even a tiny fraction of an ohm of resistance generates a massive amount of thermal energy. And this heat is generated every single time the owner drives the car, every time they accelerate to merge onto a highway, and crucially, every time they plug into a high-speed DC fast charger. Month after month, thermal cycle after thermal cycle.
It just keeps baking.
Yeah. Now, copper is an exceptional conductor of electricity, but it is equally exceptional as a conductor of heat.
Oh, I see where this is going. So the copper bus bar isn't just carrying the electricity. It's acting as a thermal highway, actively pumping that friction heat directly away from the loose bolt.
And unfortunately, it often conducts that localized heat straight down the bus bar and directly into the internal highly sensitive structure of the high-voltage relay itself.
The switch we were just talking about.
Yes. Deep inside that relay are high-precision mechanical springs made of specially tempered steel. The entire safety function of the relay depends on these springs. Their job is to forcefully and violently snap the contacts apart the millisecond. The magnetic coil is de-energized.
But prolonged high-temperature heat destroys the temper of spring steel.
Exactly. It causes deep mechanical fatigue and initiates a metallurgical process called annealing.
Annealing?
Yeah, the constant influx of heat fundamentally alters the microscopic crystal structure of the steel spring. It relaxes the molecular bonds, robbing the steel of its temper and its tension. Slowly, over months of driving, it lowers the spring's critical rebound force.
I really need to pause and emphasize the scale of this for you. A single, slightly under-tightened bolt, torqued by a robotic arm on a Tuesday morning at a factory in a different country, can quietly act like a tiny heater, slowly cooking a heavy-duty high-voltage switch from the inside out.
It's silent, invisible damage.
It ruins the tiny spring over the course of a year and eventually causes the entire ASIL-D safety system to fail. That is the definition of a cascading failure.
It really is. The spring becomes sluggish. It loses the aggressive mechanical snap required to pull the heavy contacts apart faster than the arc can form. So when the driver turns the car off and the command comes to open, the contacts pull away lazily. That slow, hesitant separation allows a miniature DC arc to form and sustain itself just a fraction of a millisecond longer than it should.
Just long enough to do damage.
Yes. This creates tiny, microscopic welds on the silver surface. Over time, these micro welds accumulate, creating a sticky friction, until one day, the severely weakened spring simply lacks the physical force to break the micro weld. The contactor remains permanently stuck.
It really highlights how deeply interconnected the mechanical and the electrical worlds are in EV architecture. You can't just write brilliant software. You have to be absolutely flawless at turning a wrench.
Absolutely.
Which brings us to a terrifying operational question. If the physical switch has literally melted into a solid block of metal, the system can't just try to open it again. A welded switch looks, acts, and conducts electricity exactly like a closed switch.
A physical weld offers no digital error code on its own. It's just a piece of metal doing what metal does, conducting energy. This leads us to a critical engineering challenge. How does the vehicle's central brain even know this silent, hidden weld has occurred? And more importantly, what drastic vehicle-altering measures does it take to save the occupants when it finally discovers the truth?
Because if the car doesn't know, and you walk away into your house like we described in the opening, the high-voltage lines running under the floor of your garage are still completely live.
Exactly.
A first responder might cut into the car at an accident scene, assuming it's depowered. A mechanic might go to work on it the next day. It remains an active ASIL-D level threat.
Right. So to combat a silent ASIL-D threat, automotive functional safety engineers implement a strategy called dual independent diagnosis.
Dual independent, okay.
The vehicle's computing architecture cannot trust a single point of data. It relies on two totally separate, technically distinct, independently verifying methods to check if that contactor is actually open.
Because it just can't risk being wrong.
Exactly.
Yeah.
The first is a purely physical hardware method, the auxiliary feedback check.
I love the mechanics of this. I mean, how do you verify the status of a giant switch without trusting the electrical flow through the switch itself? You basically build a mechanical snitch into the architecture.
A snitch pin, yeah. Inside the hermetically sealed casing of the high-voltage contactor, Engineers install a secondary, incredibly tiny low-voltage switch known as an auxiliary contact.
Okay.
This tiny switch is physically tethered, mechanically linked by a rigid, non-conductive rod directly to the massive high-voltage main contact armature. They are bound together. They move as one single, inseparable physical unit.
So where the big high-voltage contact goes, the little low-voltage contact is absolutely forced to go.
Right. Now, when the BMS decides to shut down the car, it cuts the 12-volt control power to the electromagnetic coil that normally holds the heavy relay closed against the spring pressure. The springs are supposed to violently push the contacts open. In that exact millisecond, the BMS processors look at the separate voltage signal coming from the tiny auxiliary pin.
And because it's a low-voltage pin, operating on simple 12-volt logic, the computer can read it safely, instantly, and constantly without being exposed to the 800-volt battery.
Yes. If the BMS has actively cut the power to the coil, expecting the switch to open, but that tiny auxiliary pin is still sending a continuous voltage signal saying, hey, I am physically still in the closed position, the software instantly deduces the mechanical reality.
The big contact didn't move.
It didn't move. It must be physically melted shut.
It is brilliant in its simplicity. It's a physical, mechanical tether. But you mentioned dual independent methods. What if the little plastic tether rod snaps from vibration? What if the tiny switch gets stuck itself? The hardware check is still a physical mechanism that can fail.
That is precisely why the software steps in with an entirely different mathematical approach. The dynamic voltage timing diagnosis.
The software check.
Right. This is a purely electrical system-level check. Let's go back to your garage scenario. You press the power button to turn the car off, and event engineers call IGOF, or ignition off. The BMS commands the contactor to open.
It assumes the contactor opened, but it needs an independent way to verify the high voltage line is actually dead.
So it turns its digital attention downstream, past the battery, looking deep into the inverter side of the circuit. Specifically, it starts monitoring the voltage of that massive DC link capacitor we discussed earlier.
The hydraulic accumulator from our analogy.
Exactly. Now, in a healthy, normally functioning system, the very moment the battery is physically disconnected by the contactor, dedicated high-wattage discharge resistors located inside the inverter immediately begin draining the immense residual electrical power out of that capacitor.
So refining our hydraulic analogy, it's like shutting the main supply valve and simultaneously opening a dedicated bleed valve at the bottom of the tank. The pressure in the tank should drop rapidly and predictably.
Yes, the software processors sit there and actively monitor the link voltage decay curve. It expects a very rapid, mathematically predictable drop in voltage over a few hundred milliseconds. However, if the main contactor has welded shut, the main high-voltage battery is still silently, aggressively feeding unlimited power into the circuit.
The main supply valve is still jammed wide open, so the bleed valve is draining fluid, but the tank is instantly refilling. The pressure never drops.
If the software watches that link voltage decay curve, and the voltage stubbornly stays above a critical safety threshold typically defined in safety standards as anything above 60 volts for longer than the calculated discharge time window, the system has its irrefutable independent proof.
The circuit is still live?
The circuit is still being fed power. The main contactor is fundamentally welded.
Okay, so the car has run its dual checks. It's read the physical snitch pin, it has mathematically analyzed the voltage decay curve, and the processors reach a terrifying conclusion. We have an active P0A2A P0AA1 fault. The primary safety switch is welded solid. What actually happens next? Does, an alarm go off on the user's phone?
Oh, the reaction is far more severe and instantaneous than a simple user alarm. This diagnosis triggers the permanent lockdown protocol, which is the absolute cornerstone of the vehicle's fail-safe strategy.
The lockdown.
Remember, we're operating under an uncompromising ASIL-D protocol. Once this specific fault is confirmed by both independent methods, the BMS rigidly, permanently locks down the entire vehicle's state machine.
For listeners who might not be software engineers, a state machine is the fundamental logic architecture that dictates what the vehicle is physically allowed to do. It controls the transitions from parked to ready to drive to charging.
And it locks it down hard. The BMS immediately writes what's called a permanent diagnostic trouble code, or a permanent DTC, incredibly deep into its non-volatile EEPROM memory.
It's permanent.
Yes, this is not like a standard check engine light caused by a loose gas cap, which you can clear by unplugging the 12-volt battery or using a cheap $20 OBD2 scanner from an auto parts store.
It is written in digital stone. It survives complete power losses.
The state machine strictly forbids the transition to the next ready power-on sequence. If the driver gets back in the car 10 minutes later and tries to start it, the vehicle will absolutely refuse to close any other relays or activate the drivable state.
Wow.
Furthermore, and crucially, it totally blocks the onboard charger from accepting AC power, and it severs all communication with DC fast chargers. It will not accept a single watt of power from the grid. The car is, for all intents and purposes, permanently bricked.
Bricked, meaning the $70,000 piece of advanced engineering is now a very heavy, very expensive paperweight sitting in your garage.
It is a massive inconvenience, yes, but it is entirely necessary to protect the human user. It requires a flatbed tow to a highly certified repair facility. It requires the physical unbolting and replacement of the entire high-voltage relay module.
Right.
And it requires a specialized, factory-level encrypted software tool to interface with the BMS and reset the permanent code. It's an extreme, costly reaction, but it unequivocally prevents the vehicle from being driven at high speeds with a compromised safety system.
Because it's too dangerous to drive.
Exactly. And most importantly, it prevents a high-voltage charging station from pumping massive thermal energy into a battery pack that has lost its physical ability to stop the charging process and protect itself from overcharging and thermal runaway.
I deeply respect the absolute ruthlessness of that software logic. You are not safe, therefore you are not moving, and you are not charging, period.
That's the ASIL-D mentality.
But as I was reading through the engineering use cases, I found a scenario where that thoughtful, deliberate software logic is completely useless. Everything we just discussed assumes the car is sitting peacefully in a garage or idling at a stoplight with plenty of time for computers to think. What happens if the contactor welds during a massive, violent physical crash?
That is the ultimate nightmare scenario for functional safety engineers, and it forces the introduction of the third most dramatic element of this safety architecture, the pyro-fuse.
The pyro-fuse.
We refer to it as the nuclear option.
The nuclear option.
Yeah.
That does not sound like a standard automotive component.
Let's construct the scenario. The vehicle is in motion at highway speeds. A catastrophic electrical event occurs, perhaps a massive, sudden short circuit caused by road debris violently piercing the armored battery casing. And this short circuit causes a massive, instantaneous inrush current that instantly welds the main contactor shut.
Okay, bad situation.
Simultaneously, or milliseconds later, the vehicle is involved in a severe, high G-force physical collision.
So the primary mechanical relay is utterly useless. It has melted into a solid block, freely conducting thousands of amps of energy from the battery right into the crushed chassis. The structural integrity of the car is actively being compromised.
Right.
The BMS software can't just brick the slut machine to save the car here because the energy is already flowing, sparking, and tearing through the crushed metal.
Exactly. In that specific millisecond, thoughtful software logic is far too slow, and the primary mechanical switches are dead. The vehicle desperately needs a way to instantly sever a thick copper cable conducting hundreds of amps, and it needs to do it before a fire starts. Enter the pyro-fuse.
Pyro, as in pyrotechnics, fire and explosives.
It is exactly what it sounds like. It's a pyrotechnic fuse. This is a secondary, highly active physical safety mechanism. It's a specialized, hermetically sealed component integrated directly in line with the main high-voltage copper bus bar.
Okay.
And critically, its trigger mechanism is not relying on the battery computers. It is hardwired directly via a dedicated physical line to the vehicle's restraint control module, or the RCM.
The RCM, that's the dedicated computer that analyzes G-forces and decides exactly when to detonate the airbags to save your life.
Yes, it relies entirely on the vehicle's network of extreme G-impact sensors and accelerometers. If a severe structure-compromising crash occurs, or if the internal battery sensors detect an unsurvivable overcurrent event happening simultaneously with a known welded contactor, the system entirely bypasses the normal calculating BMS software logic.
The vehicle just stops trying to calculate math and reacts to survive.
Exactly. The RCM sends a massive hardwired voltage pulse directly to the squib inside the pyro-fuse. Inside that sealed fuse, housing is a miniature, precisely calibrated chemical explosive charge.
Wow.
The charge detonates instantly. The kinetic energy of the explosion physically tears the thick, high-voltage copper conductor violently apart. Furthermore, the mechanism uses the explosive force to drive a solid wedge of non-conductive, arc-quenching material directly into the newly created gap to physically smother and extinguish any potential plasma arc.
I really need to pause and examine the timeline of this. You're talking about intentionally detonating a chemical explosive charge deep inside a battery pack that is completely packed with highly volatile, flammable lithium-ion cells.
Yes.
And according to the engineering specs, this entire process from the crash detection to the explosion severing the power happens in under 2 milliseconds.
2 milliseconds.
2 milliseconds is basically imperceptible to human consciousness. The blink of a human eye takes between 100 to 400 milliseconds. Why on earth does it need to be a physical explosion? Is the danger of a DC arc in a crash really so immediate and catastrophic that we have to blow up our own electrical architecture to stop it?
It is an absolute non-negotiable necessity. In a severe, crushing crash, every single millisecond that high-voltage power remains active from the battery is a millisecond where crushed, deformed metal chassis components could become electrified.
Right, electrocuting anyone touching the car?
It is a millisecond where a severed high-voltage cable could arc violently against a ruptured cooling line, or worse, directly against a crushed lithium-ion cell, initiating an immediate, uncontrollable, and unsurvivable thermal runaway fire.
So the explosion is not just about saving the battery hardware, it's about ensuring the entire metal frame of the car doesn't electrocute the trapped occupants or the first responders running up to the vehicle with metal tools.
Exactly. Because a standard mechanical relay, even when operating flawlessly with zero microwelds, relies on springs moving a heavy metal mass. That physical movement takes time, often 20 to 50 milliseconds, to physically pull the circuit open far enough to quench an arc.
Which is way too slow.
Way too slow. In the event of a catastrophic dead short across the battery terminals during a crash, 50 milliseconds is an eternity. The current can exponentially spike to many thousands of amps in that time, vaporizing components.
That's horrifying.
The pyrotechnic detonation acts in under 2 milliseconds. It is incredibly violent, is entirely destructive to the component itself, but it mathematically guarantees that the immense flow of energy is instantly, physically, and permanently severed.
It is the ultimate expression of cutting off the infected limb to save the life of the patient. The sheer intensity of that mechanism is mind-blowing.
It really is.
We have spent significant time discussing how the car realizes it's broken, how it bricks its own software, and how it literally blows itself up if things get genuinely apocalyptic. But automotive engineers, especially those operating under the stringent Severity 9 ASIL-D safety requirements, they don't just sit around writing software to manage explosions.
No, we prefer to avoid explosions if possible.
Right. The vast majority of their engineering effort is spent trying to stop the initial weld from ever occurring in the first place. Which brings us to the design failure mode and effects analysis phase, the DFMEA. This is where we examine how engineers design the danger away.
This represents the crucial transition from reactive safety measures to proactive, fundamental physical engineering. The core engineering question is, how do we build a mechanical switch that can routinely handle the equivalent of lightning strikes without melting its own components?
Right. How do you survive the plasma fire hose?
The first physical design mechanism is endlessly fascinating. We are taming the plasma arc with pure chemistry and magnetic fields, nitrogen and magnets.
Magnets and nitrogen. Let's break down the chemistry first, because when I visualize a standard switch, like a light switch in my house, I just picture two pieces of copper or brass touching each other in the open air.
And if you attempt to use open ambient air inside an 800-volt high-current system, the physics work entirely against you.
Oh, because of the oxygen.
Yes. The ambient oxygen in the air will actively feed and oxidize the plasma arc, burning the metals faster. Furthermore, ambient humidity, the water vapor in the air, significantly lowers the electrical resistance of the gap, making it much easier for the arc to strike and sustain itself.
So just normal air is the enemy here.
It is.
Yeah.
Therefore, a true ASIL-D rated high-voltage relay is never exposed to the atmosphere. The entire contact mechanism is housed within a thick, hermetically sealed ceramic or heavy composite chamber.
They're essentially building a tiny, pressurized spacecraft environment just for the switch.
Exactly. The internal chamber, where the high-voltage contacts live and operate, is completely evacuated of normal atmospheric air during manufacturing. It is then pumped full of pure nitrogen gas, or, in some highly specialized designs, a precisely calibrated mixture of nitrogen and hydrogen.
Why specifically choose nitrogen?
Because nitrogen is fundamentally an inert gas. It lacks the chemical properties to support combustion or rapid oxidation.
Okay, so it suffocates it.
Right. By entirely replacing the reactive oxygen with inert nitrogen, you drastically reduce the arc's ability to burn the contact materials. Furthermore, the specific gas mixtures have excellent thermal conductivity properties, helping to rapidly cool the plasma. It creates a chemically suffocating environment for the spark.
Okay, that brilliantly handles the chemistry of the arc and prevents oxidation. But you still have the problem of pure electrical heat, the raw energy of the plasma leaping across the gap regardless of the gas around it. That is where the magnetic architecture comes into play.
Yes, this is where engineers utilize one of the most fundamental laws of electromagnetism, the Lorentz force.
Ugh, the Lorentz
If
force.
you recall high school physics, you might remember Fleming's left-hand rule. Engineers place incredibly powerful, rare earth, permanent magnets meticulously arranged around the outside of the steeled contact chamber.
Right. The engineering documentation calls this magnetic blowout. And when I first read that, it sounded like a cheesy sci-fi concept.
It does sound like Star Trek.
Right. I was picturing the bridge of a spaceship. Captain, the shields are failing. Activate the magnetic blowout. But in reality, it's like using invisible magnetic force fields to grab a blast of lightning and aggressively, physically rip it in half before it can melt the ship.
That sci-fi analogy is surprisingly scientifically accurate to the physical reality inside the relay. The Lorentz force equation dictates that when a charged particle, in this case, the dense stream of electrons forming our plasma arc, moves at high velocity through a strong, perpendicular magnetic field, that particle experiences a powerful physical force.
A force pushing it sideways.
Yes, this force pushes perpendicular to both its direction of travel and the magnetic field lines.
So the electricity is desperately trying to shoot straight across the shortest path, directly across the tiny gap between the contacts.
But the intense magnetic field aggressively pushes that stream of electrons violently to the side. The exact millisecond the contacts begin to pull apart and the DC arc forms, the permanent magnetic field grabs that plasma arc and stretches it violently outward, bowing it and bending it into a massive elongated loop away from the center of the contacts.
And because the arc is being physically stretched outward, the electricity has to travel a much further distance to keep the circuit alive.
Exactly. By forcibly stretching the arc, you exponentially increase its overall electrical resistance. As the resistance rises, it requires more and more raw system voltage to sustain the plasma across that longer distance.
And eventually it just runs out of juice.
Very rapidly, the arc stretches so far that the available battery voltage can no longer overcome the resistance. The plasma simply runs out of energy to bridge the gap, and it snaps. The arc is utterly extinguished.
And this entire chaotic, violent process happens in milliseconds.
We are talking fractions of a single millisecond. The magnetic blowout architecture rips the arc apart so incredibly fast that the specialized silver tungsten alloys on the contacts literally do not have enough time to absorb the intense thermal energy and reach their melting point. The arc is blown out before the liquid phase can begin, preventing the metallurgical bond from ever forming.
That is just an incredibly elegant piece of engineering, using the fundamental passive physics of electromagnetism to actively fight a volatile electrical problem.
It's pure physics.
But that's purely the hardware side. The vehicle's software architecture also plays a massive proactive role in preventing the arc from ever forming in the first place. The next major DFMEA strategy is zero current switching.
Right, because software discipline is often the most effective safety tool. The absolute best way to survive a high-voltage plasma arc is to mathematically ensure you never create one. The BMS operates under a rigid, unbending, hard-coded software rule. Under normal operating conditions, it will absolutely refuse to open the main contactor if the system is actively under a heavy electrical load.
So if you are driving down the highway and the motors are pulling 300 amps of power and you somehow glitch the car or you panic and hit the power button repeatedly, the computers won't just immediately yank the physical switch open and create a massive 300 amp fireball inside the relay.
It will never allow that. The software coordinates a highly synchronized shutdown sequence. Before the BMS ever cuts the 12-volt power to the relay's electromagnetic coil, it first sends a high-priority message across the CN bus.
The vehicle's network.
The controller area network bus, yes, the ultra-fast deterministic central nervous system of the vehicle. The message goes directly to the inverter and the motor controllers. The command is absolute. Drop all power draw immediately.
It tells the massive electric motors to instantly stop drinking the electricity.
Exactly. The inverter uses its massive silicon carbide transistors to instantly shut down the flow to the motors. Meanwhile, the BMS waits. It actively monitors the highly precise current sensor located on the main high-voltage line.
It's watching the power drop.
It watches the current plummet from 300 amps down to 100, down to 10. It waits and verifies until the active power draw is completely zero, or realistically, validated to be safely under 1 single amp.
It waits until the high voltage line is completely quiet and devoid of energy momentum.
Only when the processors verify that quiet state will the BMS de-energize the coil and allow the mechanical springs to push the massive relay contacts open.
And because it's quiet, no arc forms.
Because there is virtually zero current flowing at that exact moment, there is no electrical momentum, there is no plasma arc. It is a completely peaceful, harmless, cold mechanical separation.
That makes total logical sense for the shutdown sequence. But what about the power-on sequence? We spent a lot of time earlier discussing the pre-charge failure, the empty hydraulic accumulator, and the devastating inrush current. How does the software design actively protect against that specific threat?
That is managed by a highly aggressive software loop known as the 300 millisecond pre-charge check. It is a game of high-frequency paranoid surveillance.
Paranoid surveillance, I like that.
It's true. When you press the brake pedal and initiate the power-on sequence, the BMS closes that small secondary pre-charge relay we discussed, letting the electricity slowly fill the inverter's massive capacitor through the restrictor resistor.
The tiny bypass valve starts slowly filling the tank.
But the ASIL-D software does not blindly trust that the resistor is functioning correctly. It initiates an internal stopwatch. The software demands that the measured voltage in the bus capacitor must climb to exactly 95% of the main battery pack's total voltage, and it must accomplish this within a rigidly defined time window.
And that window is fast.
Often, this window is precisely 300 milliseconds.
300 milliseconds is incredibly fast for a massive capacitor to charge. What happens in the microprocessor if the stopwatch hits 300 milliseconds and the capacitor voltage is only reading, say, 50% full?
The microprocessor instantly triggers a critical abort sequence. The logic assumes something is profoundly, dangerously wrong. Perhaps the physical resistor has burned out and increased its resistance, or perhaps there is a massive short circuit somewhere in the high-voltage architecture that is actively draining the power as fast as the pre-charge circuit can supply it.
So it panics.
Whatever the underlying cause, the processor determines the environment is not safe for high current.
Because if the software were to foolishly close the main switch while the capacitor was only at 50%, the resulting inrush current would still be massive enough to overwhelm the magnetic blowouts and weld the contacts solid.
Exactly that. So when the 300 millisecond mathematical check fails, the system rigidly locks the main contactor in the open position. It completely refuses to proceed with the startup sequence. It flashes a high voltage system warning on your dashboard, but crucially, it saves the physical hardware from destroying itself in a fireball.
It is genuinely amazing how much of vehicle reliability simply comes down to clever software actively preventing the hardware from destroying itself.
It's a huge part of the engineering.
But sometimes hardware has to save hardware, which brings us back to that terrifying mechanical flaw we discussed in the beginning, the slightly loose bolt causing impedance, joule heating, and spring annealing. How do you design an elegant mechanical solution to prevent that specific danger?
You introduce a brilliant piece of mechanical anti-fatigue engineering known as the Belleville washer.
A Belleville washer. The name makes it sound delicate, but what does it actually look like?
They're also commonly known in engineering circles as coned disc springs. Instead of a standard flat metal washer that you would find at a hardware store placed under the bolt head, a Belleville washer is conically shaped.
Okay.
It looks a bit like a tiny, shallow, very thick metal volcano.
A tiny volcano. I can visualize that. A curved, conical washer sitting under the head of the bolt.
Right. When the robotic assembly arm torques the bolt down into the copper bus bar, the immense downward pressure physically flattens that conical shape out. Because the washer is stamped from highly specialized spring steel, it desperately wants to return to its natural, curved, conical shape.
It's loaded with tension.
Once flattened, it acts as a continuous, heavy-duty mechanical spring, constantly pushing back up against the underside of the bolt head and pushing down against the copper bus bar.
But why is that complex, curved shape fundamentally better than just taking a heavy, flat steel washer and tightening it down really, really hard?
It comes down to the physics of thermal cycling and the coefficient of thermal expansion. Remember, These massive battery packs get incredibly hot when you are driving hard or fast charging, and they get freezing cold when you park the car outside in the middle winter.
Right.
The copper bus bars, the steel bolts, and the plastic housings all expand and contract at completely different rates as their temperatures wildly fluctuate.
Oh, the metals are constantly moving, so if the pack gets really hot, the metals physically expand and push against each other. If it gets freezing cold, they shrink and pull away from each other.
Yes.
Over hundreds and hundreds of those hot-cold cycles, a regular, rigid, flat joint will inevitably work itself loose just through pure thermal movement.
That thermal breathing is exactly how the microscopic looseness we discussed earlier develops over time. However, if you integrate a Belleville washer into that joint, its immense trapped spring tension actively, mechanically compensates for that microscopic thermal movement.
Oh, that is clever.
If the metals shrink in the cold, the washer simply curves back up a tiny fraction of a millimeter, instantly taking up the slack and maintaining the exact same extreme continuous clamping force on the electrical joint.
It literally breathes and flexes with the temperature changes of the battery.
It dynamically flexes to maintain absolute continuous pressure. This dynamic tension prevents the contact impedance from ever rising. Because the impedance never rises, the localized Joule heating never occurs.
Which protects the springs.
Because there is no heat, the sensitive relay springs are protected from annealing. And because the springs remain strong, the contactor aggressively snaps open every single time, preventing the sluggish separation that leads to micro-welding.
It is profound. A piece of curved spring steel, probably costing less than 50 cents to manufacture, actively prevents a 1,000-degree plasma bolt from destroying a $70,000 vehicle.
It's one of my favorite engineering solutions.
That is incredible engineering. But as anyone who has worked in manufacturing knows, the smartest, most elegant design in the world, perfectly modeled on a computer screen, completely falls apart if a tired factory worker or a slightly miscalibrated automated robot makes a mistake on the assembly line on a Tuesday morning.
Which necessitates our transition into the process failure mode and effects analysis, the PFMEA. We have to answer the question, how do massive automotive manufacturers guarantee a flawless physical build at a scale of hundreds of thousands of vehicles a year?
Because you can't just blindly hope the robotic arm gets the torque right every single time. Let's look at the manufacturing controls. We just talked about how absolutely critical the clamping force of that Belleville washer is. How does a factory actually ensure every single one of those hundreds of bolts is perfect?
The manufacturing engineers recognize that traditional mechanical click-type torque wrenches are fundamentally insufficient for ASIL-D level safety components.
Why is that? I mean, a traditional torque wrench clicks when it hits the specified tightness, right? Mechanics use them to build race engines all the time.
A traditional torque wrench simply measures the physical resistance to turning. It measures friction. But what if there is a tiny microscopic metal burr left on the screw thread from machining? Or what if a single grain of debris got into the threaded hole?
Oh, I see.
The wrench will encounter massive friction as it grinds against that debris. It will quickly reach the target torque setting, and it will click, telling the operator of the robot that the bolt is fully tightened.
But it's not actually clamping the copper metals together. It's just jammed and stuck on the piece of debris.
The measured torque is artificially high, but the actual physical clamping force on the Belleville washer is dangerously low or non-existent. To solve this critical blind spot, modern EV battery factories utilize torque angle dynamic dual check systems. These are incredibly sophisticated networked smart servo tools.
Torque and angle, so it's measuring two entirely different physical properties simultaneously.
Exactly. The tool measures how hard the bolt is resisting the twist, the torque, but it also utilizes ultra-precise digital rotary encoders to measure exactly, down to the fraction of a degree, how far the bolt has physically rotated into the hole.
Ah, the dual verification. So if the tool hits the heavy target torque, but the encoder says it only turned 90 degrees instead of the mathematically required 360 degrees to seat properly, the computer instantly knows it's snagged on debris or cross-threaded.
It immediately stops the line and flags a critical failure. It prevents stripped threads, it detects cross-threading, and it mathematically guarantees perfect clamping force on every single joint.
That's a foolproof system.
And furthermore, this entire system is deeply integrated into the factory's network. 100% of the dynamic tightening data, the torque curves, the angle graphs for every single bolt is recorded and permanently tied to that specific battery pack serial barcode within the factory's central manufacturing execution system, or MES.
So if a specific vehicle experiences a thermal anomaly 5 years from now on the other side of the world, the engineers can look up the exact barcode, access the MES database, and look at the digital graph of exactly how that specific bus bar bolt was tightened at 2:00 p.m. on the day it was built.
It provides absolute total traceability. It completely removes the human error and the mechanical deviations that lead to impedance heating.
Okay, that brilliantly covers the robots putting the parts together. But what about the logistics of just moving these components around the massive factory floors? The manufacturing documentation heavily emphasizes strict handling procedures. This seems like a contradiction to me.
How so?
Well, we are talking about massive, heavy industrial batteries built for cars that drive over potholes. Why do we need to treat the internal components like fragile Fabergé eggs during assembly?
It is a profound contrast that exists on the factory floor.
Yeah.
The completed battery pack itself might weigh over 1,000 pounds. The external housing is often heavily armored steel or thick extruded aluminum designed to take a hit from a boulder.
Right.
But the specific high-voltage relays inside these contactors are ultra-precision, highly delicate instruments.
Because they contain those tiny heat-sensitive microsprings and the delicate ceramic nitrogen seals we discussed.
And crucially, the magnetic blowout architecture. The powerful rare earth magnets and the tiny mechanical reeds that operate the low-voltage auxiliary feedback pin are meticulously aligned down to the micrometer at the component supplier.
So if a line worker accidentally drops the cardboard box of relays off a forklift before they even install them into the battery,
A simple, seemingly harmless drop from waist height onto the hard concrete factory floor can be completely disastrous. The impact might not crack the external plastic housing of the relay at all. It might look perfectly brand new.
but inside it's a mess.
But the kinetic shock wave traveling through the component can permanently displace those microscopic internal reeds. It can shift the physical alignment of the heavy magnetic blowouts by just a fraction of a millimeter.
And if the magnets are shifted out of alignment, the magnetic field vector changes, and they won't stretch the DC plasma arc correctly when it matters most.
The relay is fundamentally ruined, but it dies silently. If that dropped component gets installed into a battery, it might easily pass the initial basic continuity tests, but it will fail prematurely and catastrophically in the field under heavy load. Therefore, the PSMEA logistics protocols are incredibly draconian to prevent this.
Draconian in what way? How do they move them?
Factories utilize dedicated, color-coded, shock-proof logistics trays. The component packaging is deeply buffered with highly specialized foams engineered to absorb specific, harmful G-force frequencies. The automated guided vehicles, the AGVs that autonomously move the parts around the factory, are programmed to operate only on smoothed, leveled pathways to avoid vibration.
Wow.
And there is a strict zero-tolerance protocol. If a component is dropped or even heavily jarred in transit, it is instantly quarantined and scrapped. You simply cannot risk installing an ASIL-D safety component that has sustained unquantified, unmeasured G-shock.
It borders on obsessive paranoia, but when the stakes are ASIL-D, it absolutely has to be. Let's move to the end of the manufacturing line, the end of line, or EOL, torture test. The battery pack is fully assembled, the torque angle bolts are perfectly verified, the fragile relays are safely installed. Before that pack gets bolted into a car chassis, it has to pass the final exam.
The end-of-line testing for the high-voltage architecture is where the theoretical engineering meets physical reality. Every single assembled system, 100% of the production volume, no sampling, undergoes highly rigorous dynamic welding and mechanical timing checks.
Mechanical timing checks, so they're essentially testing the stopwatch functions we talked about earlier.
They are actively measuring the physical mechanical latency of the relay itself. The automated EOL testing station applies the 12-volt control power to the electromagnetic coil, and it uses ultra-fast, microsecond-level oscilloscopes to measure exactly how long it takes for the massive high-voltage contacts to physically close, and exactly how long it takes the tiny auxiliary feedback pin to register that closure to the computer.
So they are validating that the physical non-conductive tether hasn't been bent, snapped, or compromised during the assembly process.
Correct. But they also perform a highly sensitive check for what engineers call sticky friction.
Sticky friction.
Yeah. They apply tiny, very precise, low-voltage test currents through the main high-voltage system and then command the relay to open. They use the oscilloscopes to analyze the microsecond decay curve of that test current to ensure the internal mechanical springs rebound perfectly and aggressively.
Looking for any lag.
If the oscilloscope detects a single millisecond of latency, a tiny microscopic hesitation in the spring's movement, indicating excessive internal friction, or perhaps a micro-weld forming from a tiny factory flaw, the automated system instantly catches it and fails the pack.
So they're actively hunting for the mathematical ghost of a failure before the failure even physically manifests.
The goal is to intercept the latent hidden defects, 100% of them, before the battery pack ever leaves the manufacturing facility.
Okay, let's review the journey so far. The initial design is locked in. It utilizes Lorentz force magnets, inert nitrogen gas, and incredibly clever software sequencing. The factory assembly line is utterly perfect, obsessively watching every single bolt angle and microsecond of latency. But before this entire vehicle architecture ever reaches the driveway of you, the consumer, the validation engineers, have to prove it all works.
Yes, the final trial.
They have to deliberately, aggressively try to destroy the system in the laboratory to prove their math and their manufacturing processes are actually right.
We have finally arrived at the design verification plan and report phase, known as DVP&R. This is where validation engineering becomes intensely physical and almost theatrical in its aggression against the hardware.
I love the idea of theatrical aggression in engineering. Let's look at the first major validation test, the hot switching fatigue test. We spent the first part of this deep dive talking about how chemically and electrically terrible hot switching is. This is where they intentionally do it on purpose, right?
They do it thousands of times. Validation engineers utilize a massive, highly specialized piece of laboratory equipment called a BDU dynamic test rig, the battery disconnect unit rig. They take the freshly manufactured contactor and they place it inside a heavy-duty environmental test chamber. They then bake the chamber to a constant searing 85 degrees Celsius, which is roughly 185 degrees Fahrenheit.
Wait, so they are deliberately simmering the component in extreme desert heat to weaken the springs and expand the metals before they even start the electrical tests?
Absolutely. Thermal stress represents the absolute worst-case operating environment for resistance and mechanical fatigue. While the component is baking in the oven, the massive power supplies of the test rig pump the absolute maximum working voltage of the vehicle architecture, usually a continuous 400 volts or 800 volts depending on the specific car, and they push a staggering 400 continuous amps of current through the closed contactor.
400 amps of continuous current. That is an enormous, terrifying amount of raw energy flowing through that relatively small switch.
And then, while that immense current is flowing at absolute maximum capacity, the computers intentionally command the relay to hot switch. They force the contacts to rip open under the full 400 amp load.
They intentionally create the devastating DC plasma arc, the thousands of degrees of localized heat, right there inside the 185-degree oven.
They rely entirely on the internal nitrogen chamber and the passive magnetic blowouts to extinguish the lightning bolt before it destroys the rig. And they don't just do it once to see if it survives. The automated rig forces the component to violently hot switch once every single minute for tens of thousands of continuous grueling cycles over several weeks.
That is just brutal physical punishment. It's like hitting a delicate watch with a sledgehammer every single minute for weeks on end. What is the actual passing grade for a test this violent? Does the component just have to not melt into a puddle of liquid silver?
The pass criteria are incredibly stringent and mathematical. After enduring tens of thousands of violent plasma arcs, the test rig measures the dynamic contact resistance of the main high-voltage pins. The electrical resistance must step 0.05 milliamps.
0.05 milliamps. That is virtually zero measurable resistance.
If the resistance rises even slightly above that microscopic threshold, it mathematically proves the silver-tungsten alloys have suffered severe microscopic melting. It means the surface is now jagged, creating a poor connection that will inevitably lead to joule heating in the real world.
Right.
Furthermore, passing the electrical test is not enough. The engineers physically take a saw and tear the contactor apart after the test is complete. They place the tortured contact plates under high-powered microscopes to visually verify there is no severe loss or pitting of the critical alloy material. The metallurgy has to survive the torture chamber and remain effectively pristine.
It is unbelievable that human-made materials can survive that. But let's dramatically escalate the torture. Let's move to the Pyro-fuse crash test. Earlier, we talked about the vehicle intentionally blowing up its own circuitry if it is in a massive crash with a welded relay. How do you possibly validate that system without physically destroying a brand new $70,000 car every single time you run a test?
You simulate the absolute worst-case variables on a highly specialized test sled or laboratory rig. Engineers intentionally take a brand new, perfectly healthy high-voltage contactor, and they use external, high-power industrial welding equipment to physically permanently melt and weld the main silver contacts perfectly shut.
So they artificially, deliberately create the exact P0A1 permanent failure we have been discussing?
Exactly. They intentionally build a fundamentally broken, highly dangerous system. Then, they power the rig up. Massive, uncontrolled current is flowing through the welded relay. The system physically cannot turn the power off because the primary switch is a solid block of metal. Then, the validation engineers electronically inject a fake high-fidelity airbag crash signal, the RCM crash flag, directly into the vehicle's network harness. In other tests, they might physically drop a massive copper bar across the terminals to induce a catastrophic physical short circuit across the high-voltage bus bars.
I just have to point out the absolute irony and sheer brilliance of this engineering process. We literally spend millions of dollars and thousands of hours building highly sophisticated, pristine ASIL-D safety systems with rare earth magnets and hermetically sealed nitrogen chambers, only to take them into a lab, intentionally weld them into a broken state, and then actively crash test the software on purpose. It is like building an incredibly elaborate high-tech escape room just to prove to yourself that the emergency fire axe actually breaks the glass.
It is the only scientifically valid way to prove the secondary safety net holds when the primary tightrope fundamentally snaps. During this simulated catastrophic crash, engineers utilize high-speed data acquisition systems, incredibly high-fidelity oscilloscopes that sample the electrical voltage and current millions of times per single second.
What exactly are the engineers looking for on those oscilloscope screens?
They are watching the precise timeline of survival. They have to mathematically prove that the BMS software instantly recognizes the injected crash flag, immediately overrides all other pending software protocols, sends massive firing voltage pulse to the Pyro-fuse squib, and that the chemical explosive charge detonates and physically blows the thick copper circuit entirely apart.
And the timeline they are obsessively looking for on the graph is that critical 2-millisecond window you mentioned earlier.
The oscilloscope traces must definitively show the massive current dropping from thousands of amps to absolute zero in less than 2 milliseconds. But there is another, equally critical pass criterion for the explosion itself. The violence must be entirely contained. The pyrotechnic detonation inside the fuse cannot shatter the external plastic housing, it cannot expel shrapnel into the battery pack, and the heat of the explosion cannot carbonize the surrounding electrical insulation.
Right, because if the explosion designed to stop a fire actually blows up the housing and ignites the lithium-ion cells next to it, the safety mechanism caused the exact catastrophe it was trying to prevent.
It must be a perfectly clean, totally contained, microscopically precise controlled demolition that definitively severs the power without collateral damage.
It is a microscopic controlled demolition inside a moving vehicle. Incredible. Okay, the last part of the validation torture chamber. We prove the physical hardware blows up nicely and cleanly. How do they rigorously test the massive software logic architecture without constantly blowing things up and starting over?
They utilize an incredibly powerful piece of technology called hardware-in-the-loop, or HIL, simulators. Imagine a massive bank of supercomputers that are intricately programmed to mathematically emulate every single electric motor, every single lithium-ion battery cell, every temperature sensor, and every wire in the entire electric vehicle. They take the actual physical BMS computer brain, the actual silicon chip that will go into a car, and they plug it directly into the simulator.
So the car's physical brain thinks it is driving a real car down a real highway, but it is actually just playing an incredibly complex, highly realistic video game generated by the supercomputers.
And the validation engineers are the ones controlling the parameters of the game, intentionally acting maliciously. They actively try to trick the software. They intentionally fake the pre-charge failures we discussed. They tell the supercomputer to pretend the voltage difference across the contactor is dangerously high, creating a mathematical delta V greater than 5%, perfectly simulating a burned-out pre-charge resistor.
They are actively trying to trick the BMS into making a fatal error, trying to get it to close the main switch and cause a massive simulated weld.
They closely monitor how the software architecture reacts to the fake danger. They verify the rigid 3 strikes and you're locked out logic. The software must attempt the pre-charge sequence, fail, mathematically realize it failed, safely abort the sequence, and after a precisely calibrated number of retries, it must completely lock the state machine, throw the permanent P0AA1 error code into memory, and absolutely refuse to close the main contactor.
They definitively prove the software cannot be fooled into a dangerous state. What about the manufacturing assembly deviations? We keep coming back to those loose bolts on the bus bars causing impedance. How do you test for a manufacturing failure in a computer lab?
This is perhaps the most impressive closure of the engineering loop, connecting the initial design, the manufacturing floor, and the final validation. In the physical testing lab, engineers go to a replica battery assembly station. They intentionally, maliciously misassemble the battery packs.
Wait, they build them wrong on purpose.
They take those critical, heavy copper bus bar bolts and they deliberately over-torque them by 150%, actively risking thread sharing and fracturing the Belleville washers. Then they take other critical bolts and severely under-torque them by 50%, mathematically guaranteeing they are loose and will cause high impedance.
They are intentionally building physical time bombs.
They do this to rigorously prove the absolute efficacy of the factory's automated end-of-line testing stations. They take these intentionally sabotaged, dangerous battery packs and they run them through the actual EOL automated testers used on the factory floor.
And the EOL testers have to catch every single one of the sabotaged packs.
100% of them. The validation process proved that the micro-ohm resistance checks and the oscilloscope timing checks we discussed earlier will successfully, predictably detect any tiny resistance spike over 0.05 millions caused by those intentionally loose bolts. They use complex statistical analysis on the results to prove the process capability, a metric known as Shree-peak, remains above a highly stringent statistical threshold of 1.67.
A C-peak of 1.67. For those of us who haven't taken a heavy statistics class recently, what does that actually mean in plain real-world English?
It means the manufacturing process is so deeply, tightly controlled and the automated testing is so relentlessly rigorous that the statistical probability of a physically loose bolt making it out of the factory doors and into a customer's vehicle is less than 1 in several million. It definitively proves the factory assembly process is as robust and reliable as the theoretical engineering design itself.
Okay, let's take a collective breath here. We have covered a truly massive amount of technical ground today. Let's bring this deep dive back to the listener's daily life, back to that dark, quiet garage we started in.
We began by recognizing the entirely invisible, silent danger of a welded contactor, the dreaded P0A2A P0AA1 fault. We explored the terrifying reality that the physical switch meant to cut the high voltage power has secretly melted into a permanent, highly conductive bridge.
We traced that nightmare scenario all the way back to its physical roots. We explored hot switching, the physics of DC plasma arcs that act like miniature lightning bolts instantly melting advanced silver tungsten alloys. We looked at the algorithms behind pre-charge failures, and we even examined the tiny cascading butterfly effect of a slightly under-tightened bolt, slowly cooking a piece of spring steel over months of highway driving.
But we also extensively explored the immense, deeply layered fortress of ASIL-D functional safety engineering, designed to aggressively counter those threats. We look at the software watchdogs mathematically measuring voltage decay curves. We examine the physical auxiliary tethers acting as internal mechanical snitches. We discuss the uncompromising permanent lockdown state that permanently bricks a compromised vehicle to protect the human user.
And we marveled at the incredibly elegant physical designs. Tiny, hermetically sealed ceramic chambers, completely evacuated of oxygen and filled with inert nitrogen gas. Invisible magnetic force fields utilizing the Lorentz force to physically rip plasma arcs apart in milliseconds. Simple, brilliant Belleville washers breathing and flexing with the extreme thermal expansion of the heavy copper battery internals.
Not to mention the obsessive controls on the factory floor. The advanced torque angle smart tools verifying every tiny fraction of mechanical rotation. The draconian, shock-proof logistics treating massive industrial components like delicate Fabergé eggs, and the microscopic end-of-line oscilloscope testing catching resistance changes before they even become problems.
And finally, the sheer violence of the torture testing. Baking crucial components in high-temperature ovens, forcing them to violently hot-switch tens of thousands of times, intentionally welding parts shut in a lab just to prove, unequivocally, that a dedicated pyrotechnic fuse will literally blow the solid copper circuit apart in less than 2 milliseconds if a catastrophic crash happens.
It truly is a masterpiece of deeply redundant safety engineering. Every single layer of the architecture inherently assumes the layer beneath it has already catastrophically failed.
The next time you turn off your electric vehicle, hit that power button, hear that heavy, reassuring mechanical clunk from beneath the floorboards and walk away into your house, you will hopefully have a profound, newfound respect for the invisible, silent fortress of complex sensors, inert chemistry, rigid software logic, and tiny chemical explosive charges working tirelessly in the dark to ensure the immense power truly stays off.
The total silence of a modern electric vehicle at rest is not just the simple absence of a combustion engine. It is the active, continuous result of millions of hours of obsessive engineering aggressively enforcing that silence.
It really is an incredible human achievement. But as we finally wrap up this massive exploration, I want to leave you with one final, slightly provocative thought. Something for you to mull over as you consider the fragile boundary between perfect digital software safety and the chaotic, raw physical reality of high voltage energy.
A lingering question based on the absolute final layer of defense.
We have talked extensively for the last hour about what happens if the switch internally welds shut. And we have talked about the dramatic solution of blowing up the pyro-fuse if a severe physical crash is detected by the airbag sensors. The digital system handles the electrical faults, and it handles the accelerometer crash sensors.
Mhm.
But what about the unpredictable physical reality of the chassis itself in the aftermath?
What specific scenario are you envisioning?
Imagine you are trapped in a severe, chaotic accident. The initial safety systems worked perfectly. The power was successfully cut. The main contactors opened flawlessly, or the pyro fuse blew exactly as designed. The battery is completely isolated and safe. But you are physically trapped inside the crushed cabin. A first responder, a heavily equipped firefighter, arrives on the chaotic scene. They need to physically cut into the vehicle's deformed metal frame, perhaps right near the armored battery box, using heavy hydraulic shears, the jaws of life, to get you out safely.
A highly chaotic, physically destructive, and totally unpredictable rescue scenario.
The internal software and switches did their job beautifully. But if the firefighter is violently cutting through the metal chassis and they accidentally shear through a thick, orange, high-voltage conduit that they assume is dead, how does the sleeping, damaged vehicle actively know its very physical chassis is being breached from the outside in real time? If the internal computer brains are already shut down or damaged, how does the car physically protect the rescuer holding the heavy metal cutting tool from a sudden surge?
That introduces an entirely new, deeply physical layer of functional safety.
It introduces the concept of the high voltage interlock circuit, or the 503 P0A default. It is not an algorithm. It is not a software check. It is a physical, incredibly simple low voltage wire loop that physically weaves its way through every single high voltage connector, every access panel, and every protective cover on the entire vehicle. It acts as the absolute final, fundamentally unhackable physical defense line. If that tiny wire is physically severed by a crash or snipped by a rescue tool, the battery hardware forcefully, mechanically, and immediately drops the entire high-voltage system to a safe state, completely bypassing all software processors.
It serves as the ultimate rudimentary failsafe. It is the engineering recognition that when the complex digital world eventually fails, or when the chaotic physical world intrudes violently into the system, a simple broken piece of wire might actually be the most reliable safety switch of all.
It is definitely something profound to ponder the next time you look at the sleek, seamless exterior of an electric vehicle. Beneath the shiny paint and the glowing touchscreens is a massive, complex labyrinth of traps, explosive tripwires, and ingenious physics, all meticulously designed to keep the lightning safely inside the bottle. Until next time.